Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower, and the information we're going to be covering today is not really new. It's been around for the better part of 12 to 15 years, but there's a certain amount of ambiguity if you don't travel in this section of the market that frequently as far as the available arc flash calculations. So hopefully we'll be able to shed some light on it and if not clear things up a bit, at least give you some direction. Again, my goal is not to tell you what to do, it's to make you aware of the capabilities of the tool so you can do a better job of making the decisions you have to make. So as we are inclined to do each webinar is to conduct some poll questions, and there's no obligation, but clearly it would be useful to get some feedback from the audience on this list of questions, if you would please. So the first is, how often do your arc flash projects involve elements that are greater than 15 kilovolts? And no liability or obligation, is strictly just some feedback that would help me understand the areas that maybe we need to emphasize a bit. As I mentioned, there's some ambiguity. It's more so if you don't travel in this edge of the market that frequently, and we'll talk a little bit about it, but there are some capabilities that we don't discuss that often in EasyPower that we plan to kind of drill into a fair amount. So it looks like we've got a quorum here. Thank you for participating. Here's how folks have weighed in. So this pretty much reflects what I would expect from EasyPower users. And so this should be real good information for folks that don't have to deal with high voltage that often. The next question is, what has been your primary tool for dealing with arc flash calculations in that range? And again, if you could help me out with some feedback, it would be appreciated. Again, it's the ambiguity is in literally this neck of the woods where there's very little guidance from the authorities in the industry, and they have left most of us to thrash about on our own. So not to be critical of anybody, but it is I think the issue is that the demand for testing to kind of expand the knowledge base has been more significant in the lower voltage part of the spectrum. So it looks like we have close to a quorum. Let's give this another 5 seconds. Thank you for joining us today and for participating. Okay, here's how folks have weighed in on this. And that's a pretty good distribution. And then finally, what's your main concern when we're talking about high voltage arc flash based upon the number of powered phases or powered cables that you have exposure to? And this, again, is the area where there's a fair amount of, I don't want to call it disconnect, but it's difficult to follow the train of thought based upon where we're talking about it. So it looks like we have a quorum here. Again, thank you for participating. Here's how folks have weighed in on this. Interesting division of interest here. Looks like we're pretty evenly split between single line to ground and three-phase arcs. Okay, so let's get into the meat of this, and hopefully I can make some sense of at least what I thought was confusing or what I think is confusing. So as I'm going to repeat a couple times, in the new release of 1584, which was published in 2018, they specifically make no recommendations for any arc flash calculations above 15 kilovolts. So we're left with the guidance from a couple different sources. Ralph Lee's equations have been around since the early days of understanding arc flash, and then the potential for using NFPA 70E Appendix D, what's listed there, would include IEEE 1584 extended out beyond the 15 kV. Then in the single line to ground realm, there is a fair amount of detail from the National Electrical Safety Code, which is IEEE C2, and there have been updates in 2009, sorry about my 2007, 2009 and 2012, and some of that includes tables that were published in 2009 in the NFPA 70E version, and again, they are included in OSHA regulations. Now, I describe it that way because these tables are no longer included in NFPA 70, which I think is not good or bad. It just reflects the focus of NFPA 70E to be the industrial market, and the NESC tables and the NESC documentation is focused more on utilities and transmission work. So what I plan to do is verify the method that's available to us in the calculations from the NESC data. And as I do this, you're going to see that their tables are measured or stipulated in heat flux rate, which is a per unit time measurement. And then to convert it to arc flash, we would have to use some kind of time limit. So I'm going to normalize on 1 second just so we can compare the flux rate against the arc flash calculations from EasyPower and show how these methods are good for any arc time in EasyPower, not just the 1 second. Now, the whole point about doing this is that it's well understood, and I'll get into this a little bit more, that the tables in the NESC or ANSI C2, which is the National Electrical Safety Code, were generated in part by using a commercially available software called ArcPro. And so part of my mission, if you will, is to show that EasyPower produces the same results and can therefore be used as an alternative. Okay, so the current status is there's no recommendation from 1584. The guidance that we have from Ralph Lee equations is available for a model that is 3-phase open air and good for greater than 600 volts. Again, the single line to ground is a resulting table that I mentioned is based upon available software. And I'm going to walk through some examples that show that EasyPower is good for both. Again, in the old days, in the initial release of 1584 in 2002, there was a recommendation to either extend 1584 beyond calculations beyond the 15 kilovolt range or use Ralph Lee equations. That's no longer part of the standard, and so we're left in a little bit of a quandary on what to do, which is the confusion I'm talking about. In NFPA 70E, it lists several different methodologies for doing arc flash calculations, one of which is the Ralph Lee equations, and the other is Doty papers on arcs 600 volts or less, and then the 1584. Again, it's well understood that the Lee equations are very conservative, and they're only applied over 600 volts, and they get more conservative as the voltage increases. So we can go through and calculate by hand. These are equations that are available in NFPA 70E, and it's relatively easy to see based upon extracting these parameters from EasyPower that the results quite readily match the equations. Now, when it comes time to talk about the NESC tables, again, I mentioned that in 2009, NFPA 70E appendix included this. This was stipulated to be estimated instant energy for exposure for live line work on overhead open air systems between 1 kV and 800 kV. There was actually 3 tables involved. The first one was voltages up to 1,000 volts, and we'll talk about that in a later session where we get into low voltage calculations. The second 2 tables included this one, which is specifically from 1K to 46 kilovolt range. And the notes here on the right are the specifics behind the calculation proper. They're based on 15-inch distance between the air gap, and the gap, it varies based upon the voltage range that we're in, and it's stipulated in both the CFRs and the NESC table. They were used or derived using a commercially available computer program, which is pretty common knowledge that was ArcPro. The downside to using this is it gives us a heat flux rate, so we need some way to estimate or understand the trip time for any particular fault. So there's kind of a catch-22 in applying or using this methodology. Now what I'm going to do, and then the second table for high voltage ranges from 46 kV up to 800 kV. And so I'm going to go through the preparations and show what's behind these calculations, and then show where to find that information in EasyPower, because it does the heavy lifting in the math. So again, these are all open air phase to ground arcs. The air gap is calculated by taking the phase to ground voltage and dividing by 10. At those voltages, an arc is fairly stable in terms of the resistance that air provides, and its unit of measure is the dielectric, as about 10 kV per inch. And then the distance to the employee, or the working distance, is calculated by using the minimum approach distance, which again is found in C2, and subtracting 2 times the gap. And these are all detailed in both the standards and in the CFRs. Okay, so all that is to say, I'm going to produce all these methodologies after I've calculated by hand. So here's the calculation I've gone through by hand. To get the single phase to ground, you take the phase to phase and divide by a square root of 3. I divide by the voltage by 10 to get the dielectric strength, or the air gap, and then the phase to phase conversion for the voltage has to be in millimeters. So all this boils down to a relatively minor mathematic equation to give us a specific air gap for each voltage. So here's the way we worked out minimum approach distance, or looked it up, and then developed the working distance based upon that, and 2 times the gap. Okay, with all that said, these are the results I came up with by hand calculations. And the reason for doing this is to verify the results that we're going to see in EasyPower. Okay, hang with me. In EasyPower, I'm going to set up the bus dialog as open air. And then in the short circuit options, I'm going to go to the advanced tab under Arc Flash and select under the open air to choose either greater than 1K or greater than 15K, and then do a single line to ground fault when I get into short circuit calculations. So I've developed a little 3-bus example, and I'll be more than happy to send you a copy of this as we post video to the website. Now, don't be dismayed by the fact that I'm using 2 different transformers here. These are just kind of a technique to allow me to put multiple utilities on the same one line, and they don't come into play because I keep them isolated. Now, with that said, when I set up the utility source, again, I'm in database edit, I set up the voltage and then the available short circuit current. And so in the one case, we have 50 kiloamps. Now, we don't care so much about three-phase, although we will get to it when we get to Ralph Lee. But what we're focusing on is the available short circuit current to ground for a single phase. And each of these is based upon the category that are given me in the chart. So I have one for 242K, one for 69K at 20,000 amps, and then one for 765 at 50,000 amps. All right, so that's setting up the utility source. Now, when I've defined the bus that I'm going to be calculating instant energy on, I want to describe it or define it as an open air. And then under my Arc Flash Hazard tab, I'm going to define a user-defined time of 1 second, literally just to convert the heat flux rate to instant energy and be able to compare the results against the ArcPro table. Okay, so now that I've got that done, I'm going to go to short circuit focus. Again, when we go to short circuit options, in my advanced tab, for open air buses, I want to apply the methodology for that's mentioned in NFPA 70E. So again, this is NFPA reference, and it's not picking up any of the parameters from our Arc Flash options. Okay. Now I'm going to short circuit, half cycle fault current, fault all the buses, apply a single line to ground fault. And I can see reflected my 50,000 amps, 40,000 amps, and 20,000 amps. And if I calculate instant energy, I get 25, 41, and 12. Now what I'm looking for is I go to my arrange for Arc Flash, and let's just kind of look at each one of these separately. Here's my electrode gap, and this should align with what I calculated from the lookup table or the MAD description. And here's my working distance, which should compare to the calculations I made. So let me kind of go back and find those. All right, so what I'm looking for is an air gap on the 69 kV of 101.2 and a working distance of 31 inches and the instant energy. So let's verify that I got this. All right, so I've got, let's do all three of them. Okay, so the electrode gap matches the 69 kV, the 242, and the 761 for each of the bolted fault categories. And if I want to look at instant energy, I go back to my table and I see for each of those I'm matching the instant energy precisely or exactly. Does that make sense? Now, so some things that don't come into play I'm using the lookup table or the ArcPro, and that is I don't have an Arc Flash boundary predicted from the tables, which EasyPower does, and I can adjust the time such that it's not just 1 second. It'll end up being whatever my trip time is from the one line. And so that's where we're going next. So any questions on this, let me know. Again, I may be kind of beating it into the ground. But what I want to do now is go out and look at another example that I will make available to anybody that wants to see it or use it. And again, this is a multi-sourced one line that lets me look at both the 1 second calculation. For instance, here's a 1 second calculation at 10,000 amps on a 34.5 bus. And if I look at that, it's going to be open air. My Arc Flash is set for 1 second because that's what the bus is. But at the same time, I can look at the relay results, and the setup here will indicate for my Arc Flash going to be a calculated time from the relay above. So make the difference, if I come into here, fault the bus of a single phase fault, and look at my arc flash, I can see I have the results for both a phase relay and a ground relay in this particular setup, and my trip times and my instant energy resulting from either particular fault. Does that make sense? It does to me. The point is, I can look at each one of these buses individually and see what's happening, comparing the heat flux for the lookup by using the 1 second delay, or if I can see a test time, a response time from the relay, I'll show the trip time and the resulting instant energy of that actual calculation in my system. Now, with all that said, what do you do if you've got a three-phase open air result or three-phase open air system? Well, then you're kind of stuck between a rock and a hard place, because the only thing that's out there is the Ralph-Lee equations, with the following exception. And I want to use this advisedly, and this is kind of comes back on you as to whether or not you want to use this application. And that is, if I have an open air classified single phase fault, if I use a three-phase fault instead, the multiplier that's set up is 2.2. Now, there's no authoritative reference for using these multipliers. So consequently, they can be modified. If we say, let's use 4 times. And where this shows up is now on my bus calculation, right? Instead of single phase, if I go to 3 phase, now the result will be 4 times the single phase result. Now, is that a good thing or not? It's not for me to say. There's no reference that says that's the way to do it. But it's something you may want to look into based upon what the constraints on your system are. Now, one more point before we get off of this. The same thing is true in terms of applying Ralph-Lee. So let's go back to our short circuit options, advanced tab. If I don't apply the ArcPro methodology, if we apply Ralph-Lee, and right now we're only exceeding the voltage, then the results ends up looking very large. And so they acknowledge they're ultra-conservative, and the point being is that the trip time is based upon the current that's involved in that fault, and the calculations are using that equation that I referred to earlier. Now, is that good or bad? Obviously, this is going to be way out of the ballpark, and that's why they talk about it being ultra-conservative. Dean's asking, where does the 2 come from? That's my point. It's arbitrary. There's no reference that says, okay, it should be 2 times or 3 times or 4 times. I'm just saying you may want to consider what your application is and what the rational approach between a single phase open air arc flash and a 3-phase. So it's out of thin air. It's whatever you decide it should be. Must the relay times be 1 second to use the tables? The answer is yes. In other words, the table itself, let me see if I can show you what I'm talking about. The table itself is in heat flux rate, right? And so that's calories per square centimeter per second. So these are a number that you multiply times time. And the only reason we use 1 second is to show that the numbers end up being identical to what's in the chart. Even to use ArcPro, you have to take this number and then multiply it times a percentage or the time element divided by 1 second. Does that make sense? Okay. Again, I'm not sure. I'm not telling you what to do. I'm just giving you tools that let you look at your system and verify that things either make sense or should be of a concern. So I will make both of these .dez files for those of you that have EasyPower tools. We'll make them available so you can download and then play with them yourself. I find this to be an extremely valuable one line because it has half a dozen different voltage levels and then multiple times that I can play with. Any other questions? This example or this discussion is documented in the Practical Solutions Guide to Arc Flash Calculations. It starts on page 21 and it walks through the steps that I describe. And as I say, it's been there, and the people that kind of know and love EasyPower may be familiar with it. Now, the good news is we're in the process of revising that document, and we should have it out before mid-year, but it'll reflect the changes in specifically IEEE 1584. So Victor's asking, is the 1 second therefore an important constraint to use of the table, which therefore makes it not accurate when the actual? Yeah, so just to kind of reiterate the 1 second and the table. The table is the data that's produced by ArcPro, as the understanding is. And so to make that applicable to your system, you should use the trip time for a single phase fault and multiply it as a percentage of a second. So if your trip time is 1/10 of a second, then your incident energy will be 1/10 of whatever that heat flux rate lookup is. The question is out of context, but is the Arc Flash available in hard copy? No, it's PDF, and you can print it out if you like. Okay, so there's two books in question here. There's a book that was produced by Conrad St. Pierre that is available for sale. It's $120, $130, and it's the Bible, if you will, for Arc Flash analysis. What is available on our website is called the Practical Solution Guide to Arc Flash Calculations, and it's a shortened form that's focused more on the abbreviated discussion of how to do the calculations. How do utilities use Arc Flash information? Well, so they pretty much are beholden to the IEEE C2 documentation, and their studies have been done. And when we talk about low voltage results, there are two very large utility companies that have generated or substantiated the calculations in the first table, which is a lower voltage. So utilities use that, they do exactly what I just said. For a single line to ground, they take that heat flux rate and multiply it times the trip time of the system protective devices. Okay, appreciate everybody attending today. By all means, keep track of the website. We have regional training set for the next 2 quarters. We have Arc Flash workshops coming up once a month. And if you got questions, don't hesitate to contact tech support at easypower.com. Have a good day. Thanks for joining us.